Now the last section of Learning Module 2, we're going to be talking about muscle force velocity relationships. Now what is it? When the muscle is activated, either concentrically or eccentrically, the rate of length change is significantly related to the amount of force potential. So what does that mean? When contracting concentrically against a light resistance, muscles is able to contract at a high velocity. So let's look at this. If we have concentric on one side, eccentric on the other, shortening, lengthening. And in the middle is isometric, means nothing's moving. If we look at it on the concentric side, the lighter the load, the faster we can move an object. The heavier it gets, the speed of being able to concentrically contract the muscle and move that object gets slower and slower and slower. Up to the point where it gets heavy enough, it becomes isometric. We can't move it anymore. So what happens is, after we start adding more and more to it, if we're trying to hold it up and then try to control that weight, the heavier it is, the faster or less likely we are to decelerate that object to the point where everything shuts off and it just collapses. That's what force velocity curve is. As the resistance increases, the maximum velocity at which a muscle is able to contract decreases. Now, that doesn't mean if you've got a heavy weight, you're not trying to move it as fast as possible. There's explosion in the muscle contraction, but not in the movement of the weight, depending on the load that it is. And eventually, as the load increases, the velocity decreases to zero, resulting in an isometric action, which is the middle. As the load increases beyond a muscle's ability to maintain an isometric action, the muscle begins to lengthen, resulting in an eccentric action. Now, eccentrically, slight increases in load results in a relatively low velocity of lengthening. So if you're trying to bring down a weight, like in a bench press, if you got a slight increase from isometric, you can move it slowly. But what happens when you start loading it up? As the load increases further, the velocity of lengthening will increase as well. In other words, you got a heavy weight at this particular load, let's say 300 pounds, you can lower it to your chest slowly. But what happens when you put 350 on there? You know, the heavier it gets, you're not going to be able to control it or be eccentrically be able to decelerate that weight. The heavier and heavier it gets, the less likely you will be to slow that movement, slow that weight down. Eventually, the load may increase to the point where the muscle can no longer resist, and it results in an uncontrollable lengthening or dropping of the load. It's an inverse relationship between concentric velocity and force production. As force needed to cause a movement of an object increases, the velocity of concentric contraction decreases. Somewhat proportional relationship between eccentric velocity and force production. As you increase the load there, you can't control it anymore. As force needed to control an object's movement increases, the velocity of eccentric lengthening increases, at least until the point where control is completely lost. Now let's look at the angle of pull. We previously went over this, but this is one of those things I really want you to understand, because once again, you're doing a particular movement. One of the things you do is first learn structure and function. Learn what the muscle is, learn the bones, learn the muscles, learn origin and insertion. Look at how the muscle fiber architecture, the bone, how they're pulling on the bones, what the shape of the muscle is, what the movement is, and what muscles are involved in that. There's a lot involved here. Now, the angle of pull is the angle between the line of pull of the muscle and the bone to which it inserts at. So you got origin and insertion, and what is the angle of insertion? So when it pulls on a bone, what's the angle that it's going to pull at? With every degree of joint motion, the angle of pull changes. So joint movements and insertion angles involve mostly small angles of pull. Hardly any of the muscles in the body actually pull at 90 degrees. the angle of pull decreases as the bone moves away from the joint, or what they call the anatomical position, through local muscle groups contraction. Range of motion or range of movement depends on the type of joint and bony structure. So if you look at the elbow joint, it has a limited amount of range of motion versus the shoulder, which has 360 degrees range of motion. Most muscles work at angles of pull less than 50 degrees. And the amount of muscular force needed to cause joint movement is affected by the angle of pull. So is the speed of movement as well too. Now, there are actually two components here. Let's look at this. If we look at that, we have a vertical and horizontal component. So if we do vector resolution, if we look at that, we can see the resultant vector would be right there. So this is vertical, this is horizontal, and this is the resultant force. Now if we look at the angles of pull here, we're going to look at the rotary component is always going to be the vertical component. That's the component of muscular force that acts perpendicular to the long axis of the bone. So let's look at that again. Let's look at the shoulder joint. Here's the shoulder joint, here's the upper arm, here's the elbow, here's the lower arm, and here's the hand holding a weight. The muscle will attach across the joint, and if we look at the angle of pull here, when the arm is straight down, the angle of pull is almost zero. But what happens when we bend the elbow just slightly? The angle of pull will change, and that gives that, but the rotary component will be right there. It's always perpendicular to the long axis of the bone that the muscle is pulling on. When the line of muscular force is at 90 degrees to the bone to which it attaches, all the force is rotary force. So if we look over here and look at this, when that muscle is pulling, it attaches that, when the angle of the joint is approximately 90 degrees, remember the rotary component here, here's the muscle force, here's the rotary component, and it's at 90 degrees perpendicular to the lever that's moving. At this point, we have 90 degrees. So all the muscle force is all rotary. There's no stabilizing component, there's no dislocating component, it's all rotary at 90 degrees. All the force is being used to rotate the lever about its axis right there. The closer the angle of pull 90 degrees, the greater the rotary component. So if you look at this diagram versus this one, it's the same thing. The rotary component, it's all rotary. There's no dislocating, there's no stabilizing forces, nothing. It's all rotary. Now, all other degrees on the angle of pull, one of the other two components of force are operating in addition to this rotary component. Now, rotary component continues with less force to rotate the lever about its axis when it's less than 90 degrees or greater than 90 degrees. And the second force is the horizontal. Here we have our vertical. The next one will be the horizontal. The non-rotary component is either a stabilizing component or a dislocating component, depending on whether the angle of pull is less than or greater than 90 degrees. If the angle is less than 90 degrees, the force is a stabilizing force because its pull directs the bone toward the joint axis. It's actually pulling the lower bone into the joint and it's stabilizing it. So if we look over here, here's the force of the muscle. We have at 90 degrees, we have a rotary component. And if you look at that muscle pulling this way, it's pulling the bone into the joint. So therefore, we have a stabilizing effect. There's a stabilizing force. Here's the rotary force. Here's the muscular force, so it's pulling it in. And that's at angles of less than 90 degrees. This happens not only with the elbow, but it can happen at the shoulder joint too when you're doing a pull down or an overhead press, or it can happen at the hip and the knee joint. The angle is less than 90, it's dislocated. If it's greater than 90, it means the force is dislocated, it's pulled directly the bone away from the joint axis. Both stabilizing and dislocating are parallel with the bone lever. Let's go back. Now, up here. Here's the joint, here's the shoulder, here's the elbow. The elbow is bent, greater than 90 degrees. Here's the pull of the muscle toward the shoulder. Insertion always pulls toward the origin. We still have the rotary component, which is perpendicular, but instead of pulling it into it, as we go past 90, the bone wants to pull away from it because the muscle wants to pull it away. So that would be a dislocating force. So you can see right there. Here's a stabilizing component because it's pulling in, rotary. Here's your vertical. Here's your horizontal. Here's your vertical. Here's your horizontal. And once again, we have vector resolution there. Sometimes desirable to begin with the angle of pull is about 90 degrees. If we look at that, what does that mean? Like we do a chin up. So if we're looking at doing elbow flexion, if we're hanging there this way, that's where the muscle is producing the greatest amount of force. And you've seen people do partial movements in the gym. They do bicep curls from here, they do them to here, then they do full range. But at that point is where the muscle is exerting the greatest amount of force. So if you're doing a pull-up and you start there, you can actually hang there and then come down. Or even try to pull up this way. So it just depends on what your goal is there. But at that point, it's where the muscle is exerting a lot of force. It's really hard for people to pull up to that point, but once they get there, it's easy to pull up from there. The angle makes the chin up easier because of the more advanced angle of the pull, which is what we just said. Compensates for the lack of sufficient strength to pull it up to that point. Now, let's look at uniarticular, biarticular, and multiarticular joints. Biarticular and multiarticular are basically one and the same. The uniarticular muscles, that means where the muscle crosses and acts directly only at one joint. Example, the brachialis. It attaches to the coracoid process and attaches to the middle of the arm. All it does is, its basic primary function is to do shoulder flexion. You can pull in a humerus and ulnar closer together. That's all it does. Oh, I'm sorry. Let's go back. I'm thinking of the coracobrachialis. If we look at the brachialis, it crosses the elbow joint and it's attached from the middle of the arm across the elbow joint, and all it does is does elbow flexion. Pulls the humerus and ulna closer together. That's all it does. My mistake. Biarticular muscles that cross and act on two different joints. Depending, biarticular muscles may contract and cause motion to either or both of its joints. The two advantages over uniarticular muscles: they can cause and or control motion at one or more joints, and they're able to maintain a relatively constant length due to shortening at one and lengthening at the other joint, which doesn't really happen, but what it does, it maintains a constant length. Muscles do not actually shorten at one joint and lengthen at the other, as we said. The concentric shortening of the muscle to move one joint is offset by the motion of the other joint, which moves its attachment farther away. The maintenance of relatively constant length results in the muscle being able to continue its exertion of force on the lever or bone that's moving. Now, we've talked about this before, I believe, about concurrent shift. Concurrent movement patterns occur when both the knee and the hip extend at the same time. So, if we're coming down, the hamstring is lengthening, so the quads are lengthening as well too with the trunk upright. But when we come up with the feet planted, the knee wants to extend, the hip wants to extend, and so does the trunk. That's called a concurrent shift. Now, if only the knee extension occurs, the rectus femoris will shorten, but it decreases its ability to exert force, as do the other quadricep muscles. But its relative length there, and subsequent force production capability may be maintained due to its relative length at the hip joint during extension. So it's only going to be able to do that. But if we're going up, we can actually get both muscles. It's lengthening at the knee joint, shortening at the hip. The hamstring is lengthening at the hip joint, shortening at the knee joint. So as we come up, this is extending, this is shortening, this is lengthening. So it's just the opposite effect on both sides. Now let's look at the hip and knee biarticular muscles in a soccer kick. This is called a countercurrent movement. Lower extremities. What's happening is, as we talked about this before too, as he comes back to kick, the quadricep muscle, the rectus femoris, is lengthening at both the knee joint and the hip joint. All right, but the hamstring is doing what? It's extending the hip and flexing the knee, two with its major functions. So we have active insufficiency on one and passive insufficiency at another. Passive insufficiency on the anterior side and passive on the front, active on the other. During this extremity, this lower extremity forward movement phase, the rectus femoris concentrically contracts to flex the hip and the knee. So as we come through here to kick, what's happening? The quadricep muscle, the rectus femoris, is shortening this way. So what's happening to the hamstring? The glutes and the hamstring are lengthening at the hip joint. But when we extend the leg, what's happening to this? Both sides of the rectus femoris are shortening to cause both movements. And on the opposite side, the countercurrent movement, the hamstrings and glutes, particularly the hamstrings, are lengthening. They're going to shut off so this movement can happen. Like I said, the antagonistic muscles will, what they call reciprocal intervention, occurs through reciprocal inhibition of the antagonist. They shut off. The activation of the motor units of the agonist create a reciprocal neural inhibition of the motor units on the antagonist. So as this side, the anterior side, is trying to contract, it sends a signal to shut off the antagonist. Reduction of neural activity of the antagonist allows them to subsequently lengthen under less tension. Because remember, if you're trying to lengthen the anterior side, the quad, the hip flexor and knee extensors that way, if this were to activate, it would be harder to do that movement because the antagonist would be on and it would really decrease the efficiency of that movement. We just talked about this, active and passive insufficiency. As the muscle shortens, its ability to exert force diminishes. And active, it is reached when the muscle becomes shortened to the point that it cannot generate or maintain active tension. And that would be, in this case, he's coming back, the hamstring, which does hip extension and knee flexion. It's contracting on both sides, so it's actively insufficient. It can't really go through each joint's full range of motion. But on the other side, passive insufficiency, the rectus femoris is lengthening at both joints that it crosses, but it can't lengthen all the way because if both sides lengthen, that means there's only so much you can lengthen at both joints. So the range of motion is going to change. We earlier observed that either biarticulate or multiarticulate muscles, when full range of motion is attempted at all joints crossed to the muscle, it can't be done. It just can't be done. When it crosses two joints, it can't be lengthened all the way. Like I said, the rectus femoris contracts concentrically to both flex the knee and extend the hip. You can completely perform either action at one time, but actively insufficient to obtain full range of motion at both joints simultaneously, which is what I just said. Similarly, the hamstring cannot usually stretch enough to maximally hip flex and maximally knee extension due to its passive insufficiency. As a result, it's virtually impossible to actively extend the knee fully when beginning with the hip fully flexed and vice versa. Now, this is the end of this particular learning module, and there, like with learning module 1, there's a substantial amount of online resources that you can go through if you need more visuals about these movement patterns, these muscles and everything too, and all other kinds of websites you can go to get even more information. So go through this, and once again, let's realize that structure and function, we learned that in anatomy phys, but here it's just as important as well. You have to learn bones, all the bones. Long bones, short bones, all the landmarks on them too, how they're put together, how joints are put together, muscles, origin and insertion of all the muscles that cause movement. Either primary movers, stabilizing muscles, secondary movers, and neutralizers. You have to learn all of them. The muscle fiber architecture of every muscle, where they insert at, what the angle of pull is, and how they work in cooperation with each other that cause human motion throughout all planes of motion. So we'll see you on Learning Module 3.